use the substitution y equals vx, where v is a function of x, to solve dy by dx equals x plus 2y over x. Okay, so that's to get a general solution. Part B, find the particular solution if y equals 3 over 2 and x equals 3. So we're giving the initial values, turning it into an initial value problem so we can actually find the function. Now this, using the substitution of y equals vx, this is a standard approach whenever you get what's called a homogeneous differential equation. So whenever you get something where you've got dy by dx is some sort of quotient involving x's and y's, then this approach should always reduce it to a separable differential equation where we can separate the variables and integrate both sides with respect to x. So let's just do exactly what it says, and we should actually get quite far. So part A, so y equals vx. So that is fine. You're obviously, where you see this y here, you're going to replace it with a vx. But what it doesn't cover is the dy by dx. So because we're told that v is a function of x, so if we want to find dy by dx with y being vx, then we need to use the product rule because we've got a product of two different functions of x, one of them just being x and the other one being a general function v that we don't know what it is. And we don't even need to know what it is, to be honest. But basically, think about a product. You've got two things being times together, u and v. I suppose I could have called v, but that might have been a bit confusing, so I'm just going to stick with u, v in that order. So for the product rule, we're going to need u dashed, and v dashed. Okay, so u is just v. So u dashed is going to be the derivative of v with respect to x. So that is going to be dv by dx. V, we've said, was x, so dv by dx, v dashed is 1. Right, so now we can write dy by dx. Remember, according to the product rule, it's u dv plus v du. So it would be u v dashed plus u dashed v. And when I'm talking about v, I mean the v in terms of the product rule. Okay, so that's going to be u, we said, was v, times v dashed, which is just 1, plus u dashed, which is dv by dx, times v, which is x. So I'm going to write that as x dv by dx. Okay, so now we've got a substitution we can make for dy by dx and for y. So we have dy by dx equals x plus 2y over x. I'll write that here so I don't have to keep going. dy by dx equals x plus 2y all over x. And we said that y was vx. Okay, so now we're going to rewrite this. We have a new expression for dy by dx, and we have a new expression for y. So let's just write that down. So dy by dx, we're going to write as v plus x dv by dx. So v plus x dv by dx, so that's our dy by dx, equals x plus 2y, so x is the same, x plus 2y, y is vx, so x plus 2vx over x. And you can see there's going to be a really nice cancelling of x's, so you can see the method's really starting to pay off already. But just so we are clear on what we've done, this is dy by dx equals x plus 2y over x. Okay, so it's just the whole thing rewritten, knowing that y is vx. Right, I think I'll get rid of that. Okay, so now we can cancel those x's off. So you've got 3 terms on the right-hand side. So 1, 2, 3, and x is a common factor of all of them. So we can say 1, 1, 1. 1, 1, 1. Just divide through by x on there. Okay, so we're cancelling out. It's just as though we're factorising the numerator, pulling an x out, and then just cancelling it with the x in the denominator. So now we're going to have v plus x dv by dx equals 1 plus 2v. Right, so now we can think about separating variables. So we want the v's with the dv by dx ultimately, and we're not quite ready to do that. I'm going to subtract v from both sides, and that is going to hopefully get us in a position where we're ready to move. So let's leave the x dv by dx for now. So that is going to equal 1 plus 2v minus v. So that can just be 1 plus v. Okay. So now we can put the x on the right hand side, divide through by x. We can put the 1 plus v on the left hand side if we divide through by 1 plus v. So that is going to say 1 over 1 plus v dv by dx equals 1 over x. Okay, so now we can integrate both sides with respect to x. So the integral of 1 over 1 plus v dv by dx equals the integral of 1 over x dx. So we get this lovely cancellation you should be used to by now of the dx is 1, 1. So that just says the integral of 1 over 1 plus v dv equals the integral of 1 over x dx. The integral of 1 over 1 plus v dv equals the integral of 1 over x dx. So very nice integrals. You've got on the left-hand side an integral in the form of f dash x over f of x. So that is just going to integrate to the ln of the absolute value of f of x. So this will be ln of 1 plus v. I'm not going to put a constant, remember, because we're going to have constants from both. So we only have to write it once because we could combine them anyway by addition. So that equals ln x plus c. Right, so now if I want to combine these things, okay, now remember this c is just a constant. So we're just going to let c equal ln a. So just a constant for a constant. ln of a, we're just saying exactly the value of some constant c. But we're just going to write it as ln a, and then we can combine it with the ln x. So ln, the absolute value of 1 plus v. In fact, that should be an absolute really, shouldn't it? Equals ln absolute value of x plus ln absolute value of a. Okay, now we can combine the logs on the right-hand side. We can write them as a single log just by using the first law of logs. So that is going to be equal to ln of x times a, or ax. So ln ax is equal to ln 1 plus v. Now we can undo the logs, or just equate the arguments of the logs, really. So either way, 1 plus v equals ax. Okay, so we've gotten really, really far to a general solution, but we don't want it in terms of v. Remember, this original initial value problem, it's to do with y and x, not to do with v and x. So we're now going to put this in. So y equals vx. Y equals vx. So if we wanted to put the y back in, v is going to be y over x. So we can, where we see that v, we can write it as y over x. So 1 plus y over x equals ax. And then remember, we're looking to get a general solution in the form y equals something. So we want the y on its own. Multiply through by x, that would say x plus y equals ax squared, which means that y equals ax squared minus x. And that is our general solution. which means we've finished part A, and now we can go on to the particular solution. So find the particular solution if y equals 3 over 2 when x equals 3. So part B, y equals 3 over 2 when x equals 3. Okay, so we just substitute in for x and y, equals sign. So we just substitute in for x and y. So 3 over 2 equals a times 3 squared, minus x, which minus the other 3. So 3 over 2 equals 9a minus 3, probably multiply through by 2 at this point. So that is going to be 3 equals 18a minus 6. Big A minus 6. Divide through by 3, so 1 equals 6a minus 2. 6a is going to be 3, so a must equal 3 over 6, which is 1 over 2. So the general solution was y equals ax squared minus x, which means that the particular solution will be y equals a half x squared minus x. Particular solution is y equals a half x squared minus x.